A cyclist is riding a bicycle at a steady velocity of 12 meters per second. The cyclist and bicycle have a total mass of 68 kilograms. Calculate the kinetic energy of the cyclist and bicycle. Use the equation Ke equals half times mass times velocity squared. So, very easy question for 2 marks. So, firstly, you don't need to do any unit conversions. You just have to do 0.5 for the half times mass, 68, and for velocity squared, which is velocity, just do 12 times 12, and that's how you could write it into a calculator and always get it right. So just do the velocity times velocity to get it right, which is 4,900 joules. Done. Describe the energy transfer that happens when the cyclist uses the brakes to stop. So when they're using their brakes to stop, basically, well, you've got kinetic energy or energy in the kinetic store of the wheels because it's moving, and then the brake is applied, and due to friction, that energy in the kinetic store is transferred to the environment as heat. So the thermal store, or you could say in the brake pad. So the energy in the thermal store of the brake pad increases. So you could say energy in the kinetic store of the wheels is transferred to the thermal store of the brakes. So that's how we're slowing down. Kinetic energy is reducing in the wheel, but increasing thermal store in the brakes. And remember, energy is always transferred, not destroyed or created. So if it seems to be disappearing somewhere, it's appearing somewhere else. Probably not the best use of language, but you get the idea. The cyclist starts to cycle again. The cyclist does 1,600 joules of useful work to travel 28 meters. Calculate the average force the cyclist exerts. So this is work done and distance and force. So let's have a look. So here's the equation that ties it all together. Work done equals force times distance. Now we've got work in joules, work done in joules. Force in newtons is what we're trying to work out, and obviously distance in meters. So no unit conversions, but we do need to rearrange an equation. Now, if you're not sure how to rearrange an equation, here's a nice way to do it. Just apply, if you haven't seen this before, just apply figures that make sense, like 6, 3, and 2, because 6 is 3 times 2. So if we lock these in now, so work done becomes 6, force becomes 3, distance becomes 2, and we want to work out average force, how could we rearrange this to get force? So let's move force onto the side we want. So this is what we're trying to do. This is what we want to get. So force is given a value of 3. What do we do to 6 and 2 to get 3? Well, 6 divided by 2 is 3. So work done divided by distance is force. It's a nice little technique which will make sure you get the answer right. So now we substitute the real figures in. Work done is 1,600 joules, you can see that up here. Distance is 28, you can see that up here. And so the answer is 57.14 newtons. If in doubt, just go to 2 decimal places. An athlete uses a training machine in a gym. The display on the machine shows the time spent on the machine and the amount of energy transferred during a training session. Figure 5 shows the displays for 2 different sessions by the same athlete. So you can see the time is the same. You can see in this one they transferred far more energy in the same amount of time than this one. Explain what the displays show about the average power of the athlete in each of these 2 sessions. So average power is energy transferred over time. So this one shows that there's got a greater average power because you're transferring more energy in the same amount of time. So more energy transferred in 300 seconds in first training session, so more power developed in session 1. Notice how they use using power correctly in terms of grammar is quite tricky sometimes. So look how they've expressed it. So more power is developed in session 1.